Okay, if you are able to give me detail about the question, or in case if you are able to screenshot and give me the question tutorial. Okay, so then easier for me to address, because sometimes I'm not 24 hours in front of the laptop. So when you tell me,
他其实
okay,
是有
so
说下来，只
tutorial,
是
okay, so this
我懒得
tutorial,
选，
okay,
所以我
so
就打
this
算尝试一
chapter,
下。
question number. So I will not able to recall that question. Okay, I don't download the everything in my phone. Okay, so therefore only when I'm in front of the PC, I'll be able to check which is the question, then provide you the details. Sometimes I do write. Okay, I think there's now the day there's one student from here. I think so ask me a question on electric field. I think he no beside no, beside you. Yeah. Ask me a question on electric field. Okay, so Tobogo. Okay, so I mean, then I was in a discussion meeting. So then, but then because the question was screenshot and send me, so I'm able to write the solution and then I screenshot and I take a picture and send back. Who was that? Huh? Electric field question? Oh no. Tibonge. You there? Okay. So you ask me question, you should know. You ask me. Hmm. Okay. So yeah. Okay. So okay, come. Let's go to the lesson. Chapter 5. So the last chapter, atomic and the quantum physics. So we know the structure of an atom. Okay. So here we are going to analyze more detail about the atomic nature of the material. Okay. So we are not specifically looking into the atom. So we are, I think did I start the recording just now? Okay, start recording. Because sometimes then I don't have there was one of the video, okay, so it is muted. Okay, I'm not sure which lecture. So the whole lecture, I think, because accidentally it was muted. So I didn't realize. Okay, so so that one you just see a silent video. Okay, so you're not able to hear my voice. And quantum physics. So that later we will move on, okay, to further to discuss on the part of the quantum physics. So in this chapter, at the end of this chapter, so what is important, okay, so which you need to carry, especially for the exam, is the understanding of the Planck's quantum theory, because that is very important. This is one of the theory which is gave Einstein, okay, so he won a Nobel Prize for somewhere about 1912. There's some 19, so I could not, I'm very bad in history. Okay. So he won but I know, okay, so during that time he was not well, he was sick. Okay, so towards the final, when he proved it, he was actually admitted in the hospital. Okay, he told me. So then, okay, so eventually he has managed to get a Nobel Prize for this because he's able to explain some things which is beyond what has been said by Sir Isaac Newton. So even during the Isaac Newton, okay, the quantum theory has been there. he has came up with the idea of quantum theory, but it is too much of a classical. Okay, so therefore, as the modern era of the science comes in, so Einstein, okay, with Einstein, all this Schrodinger, we probably have not heard about Schrodinger. Schrodinger is one of the person who have a lot of contribution in the field of quantum physics. Okay, so uh, many more. Okay, so they are the modern era of the scientists. So during that time, the modern quantum physics has been developed. Okay, so by Einstein. So you will look into the Planck, photoelectric effect. Oh, sorry. So the detailed experiment was actually the photoelectric effect. Planck's quantum theory is it is a theory discussion about the energy of the electromagnetic ray. And then from that, okay, so Einstein have put forward the photoelectric effect. It is also known as the Einstein's photoelectric effect. So that was the experiment that won him a Nobel Prize. So we will be studying that. That's the two main important thing. Then from that, we will move on to understand about the wave particle duality. Wave particle duality, or we can say wave particle nature. A matter which is able to show the both property as being as a wave and a particle. It's not a particle 100%. It's not a wave 100%. It can show both. Okay, so that is what wave particle duality. So the person who comes into the picture here is de Broglie. So there's a person known as de Broglie. Even the wave particle duality, it is also known as de Broglie's law. Okay, de Broglie's law. So he have explained that, for example, an electron can behave like a wave, okay, by showing some nature of a wave, and it can behave like a particle by showing a nature of a particle. So he combines the two nature and he came with a theory which is called the wave particle duality. Okay, that's then last part of the chapter. We will be looking into X-ray diffraction. But this X-ray diffraction is for your understanding purpose, the application in the medical and so on. So therefore, for the exam, okay, so the X-ray diffraction will not be tested. Okay, so take note. It is for your understanding, there's an application. But the detail about the X-ray diffraction, okay, so will not be tested in the finals. Okay, move on. Okay, I'm talking. So Planck's quantum theory. So what is Planck's quantum theory is said? Okay, so that is said by Max Planck, obviously. So that is Max Planck. I'm not sure. Okay, so that was the picture that's been shared. Okay, so Planck's quantum hypothesis. So when you say hypothesis, I suppose you all have learned this before. What is hypothesis? When you are in a procedure of an experiment, okay, when you say hypothesis, what is that? So when you are going to write an hypothesis about an experiment, so that is the initial prediction of the relation between A and B, for example. Correct. So what is the initial prediction? The initial prediction may not be correct. Okay, then only you go through the experiments. You do the experiment. And through the experiment, you have a problem statement. So after your problem statement, okay, so it goes to the hypothesis, then you go into the process of the experiment, all that procedure, you conducted the experiment, your data, then you analyze. After you analyze the data, experiment data, then only final you come to the what is that? The conclusions. So then, okay, so you will say whether the hypothesis is accepted or not. Okay, so hypothesis, the initial prediction. So according to the Planck's quantum hypothesis, the energy of the oscillations of atoms within molecules cannot have just any value. So instead, each has energy which is a multiple of a minimum value related to the frequency of the oscillation. Okay. So to put it in simple, because like the the way it is being structured looks a bit difficult to summarize for us to understand. It says that energy of a when you are referring to an atom. Okay, so in an atom, when you are referring to the electrons in the shells and so on, so they will have a specific energy. So they cannot have energy of any like range. So cannot have just any value. So it will have like a in a multiple of an integer. So from the experiment, okay, so they found out that these energies can be represented by the formula E equals to HF. Because when you are referring to the energy of electromagnetic ray, okay, so it is dependent on the frequency. And when it's dependent on the frequency, obviously wavelength can be related because we know the formula there. Okay, no. So because we understand that the speed c equals to f lambda. Therefore, the frequency is equivalent to c over lambda. So we can also substitute the frequency or equivalent to c over lambda, which is related to the wavelength. Okay, and h is a Planck constant that is obtained. For example, if we were to show how the energy of the electromagnetic ray changes with the frequency, so a graph can be plotted, okay, so based on how energy changes with the frequency. So they obtain a straight line. And finding the gradient, okay, that gives you a constant. So that gradient constant is what the Planck constant was. So then in order to form an equation, so then we have consider the constant into. So E equals to HF. But it is found that this energy is a multiple of an integer. So multiple of an integer meaning 1, 2, 3, 4, 5. Okay, if the first level energy is equivalent to 5 MeV, for example, or 5 EV, then that's the first integer. So the second integer, 2 times 5, 10, 3 times 5, 15, 4 times 5, 20. So it is always a multiple of an integer. It never falls in between. If we cannot have like 1.5 multiplied by 5. Okay, 1.2, 1. Okay, so 2.1. No, it is the integer. Okay, so there is a specific energy levels. So that is what mentioned. So therefore, you have E equals to HF. Okay, so when you put in the integer, so E equals to NHF. So the quantum number N. Okay, so N is referring to the quantum number. It is a discrete number. Okay, so Planck constant value is 6.63 times 10 power minus 34 joules second. So no need to worry about that. Okay, so that will be given in the exam. So according to, if you look at the diagram here, so Planck's quantum theory, molecules of radiating object. So these are the molecules in a particular packet or discrete of energy. And these energies can be, okay, so in a form of an integer, depends. Okay, so it can be 1, 2, 3, 4, and so on. So that is what meant by energy in a form of a integer or discrete energy. So we also call that as a discrete energy of the atoms. So what is the diagram? This diagram is a symbolically tells you the wave theory and a quantum theory. Quantum theory is the modern one. Wave theory is more classical. So, according to Newton, okay, so according to Newton, so Newton have more supported, it was talking about in wave theory, okay, whereby the energy levels, there is no specific level. It can be any continuous value. So that's why you can see the slope is like smooth. But when it comes into the modern, okay, physics, so the quantum, so then you can see there is an n which is referring to first stage, second stage, third stage, fourth stage, the steps. So meaning the energies are, they have a specific level. Okay, they cannot be a continuous. Okay. So now we come to the photoelectric effect. So what do you have learned from the first part? Okay, so we talk about the Max Planck. So Max Planck had mentioned about the quantum of an energy. That energy is have a specific level. So energy can be represented by E equals to hf. And according to Max Planck also, this energy carried by these waves, electromagnetic waves, or any form of a discrete uh, sources. So this energy carried by these sources of we can say discrete, can be also called as a photons. Photon. So when you talk about, when you refer to electromagnetic wave, so electromagnetic wave, the energy of electromagnetic wave is referred as a photon energy. So they come as a continuous ray in a discrete level. Like if you, for example, the light source here. So the light is continuously, the energy batch by batch is arriving to everyone, to me. It's not like, for example, oh, I don't have anything to throw. Okay. So they say if I throw something to you, okay. So moment when I throw, the energy is traveling, and when you capture it, it have arrived. So there is no follow-up. But if you are looking at a light, continuously the light energy is it is being traveling towards you, correct? So that's why that is a photon. When I throw a particle on an object, so I cannot call that as a photon, even though it carries an energy, because it only one. Okay, but when you are referring to photons, so it is a batch by batch of energy has been continuously arriving at a particular spot. Okay, so here when light, okay, so we are looking into the effect of photoelectric effect. So when a light, EM, electromagnetic wave, shines on a metal surface, it is been identified, okay, found that electrons are found to be emitted from the surface. There is an electron emission. Why this electron emission? Okay, so probably the electrons have received some form of an energy from this electromagnetic wave. Because these electromagnetic waves are energy, they are photons. So they supply the energy to the electrons in a metal. And when the electrons in the metal, okay, receives the energy, then what will happen is, uh, if the energy is enough, so it is able to escape from the metal surface. Okay, 924. Okay. In 5 minutes, okay, so I will let you to sign attendance and go back to your place. Okay, so then after that, I will take the attendance list. Okay, so come. So if you look at this, okay, electron is being emitted from the metal surface. Okay, move on. So emission of electrons from a substance due to the light, okay, so which is striking to the surface. So when a light source of a particular frequency arrives at a metal surface, so that will provide a sufficient energy for the electron to escape from the metal surface. So you escape from the metal surface. So if you look at it, okay, so this the electrons, when you talk about the electrons inside the metal, so these electrons will have some source of a minimum energy. So the energy that holds the electron inside the metal. So when the energy of the photon, the electromagnetic wave, okay, the light source you can also refer as a photons. When it arrives at a metal surface, then you can see the electrons will be emitted. The electrons will get some kinetic energy to escape from the metal surface. So experiment, like for example, when you look into these are the experiment, that this is actually something that is from the classical physics. Okay, so because 18, so when you talk about 18,000, okay, so which is very much earlier, so which is during the, I mean, after the Newton. So in this case, during that time, the experiment was conducted using electroscope, and when a UV light, okay, ultraviolet light is shined on an electroscope, okay, so you can see the electroscope initially there is electrons, and these electrons happen to escape. Okay, so from the electroscope when it is being shined by the UV light. Initially, okay, so you can also see the part here. Here you have these two things here. That is actually gold foil. So it is a gold foil, a very thin foil. So when the electroscope is negatively charged, when it has a negative charge, same charges will repel each other. So that's why you can see the gold foil is repelled. Okay, so they have a greatest angle between them. So this one is the gold foil. So they repel. The moment UV light is shined on it, so these electrons gain some energy and these electrons have escaped from the metal surface. So when they escape from the metal surface, the number of electrons which is remaining on the electroscope will be reduced. The intensity of the electron is reduced. Therefore, the repulsive force that is involved becoming lesser. Then you can see the gold foil falls. So you can see the angle becomes smaller. See, we don't see the electron is being emitted, but by observing these changes in the deflection of the electron, deflection of the gold foil, okay, so the angle between the foil, we know something is happening. And because initially it was charged to negative, and the deflection is reducing, we know there is a reduce in electron. Why there is a reduce in electron? Because the electrons are emitted. So that is how the idea came. Okay, so meaning something the changes taking place when light is shined on a metal. Okay, so this was in fact actually I wanted to, if you want to go, I mean experience this experiment, this one experiment can be conducted. I wanted to what's that, get equipments, okay, at least one set to conduct this experiment to demonstrate to the students. But then, due to some safety matters, okay, so I will not, what is that, able to get this because we have to use a laser source to conduct the experiment. It has to be in the dark room, and it takes quite an arrangement for us to conduct the experiment. Okay, so and therefore, I have conducted this experiment during my first year of my degree. So first year of my degree, so I've conducted the experiment. Okay, so it is took 3 hours in the morning, 3 hours in the afternoon. Okay, so to complete the experiment to get the data of a different source. Okay, so to work out to get a graph for this particular experiment. Okay, so before we go to the experiment, okay, so I'm going to stop here for a while. Okay, so okay. Who's coming in new now? After half an hour? You are late? Okay. So look at it, the point. So ultraviolet light discharges a negatively charged electroscope by causing it to emit electrons. So discharges mean it causes the electrons to be released. So it loses the charge property. So as it loses the charge property, so you can find uh, the magnitude of the force. You did your chapter electric. So the electrostatic force decreases when the density of the charge decreases. Okay. So look at this equipment. So this is a setup to conduct an experiment for photoelectric effect. It comes with a photo cell. So you have, I will just go slow to describe the equipment. So a circuit to study the photoelectric effect. Okay. So we have a light source. This light source can be known as photon. It can be represented by the formula E equals to HF. Okay, it can be represented by E equals to HF. So the electrons from a current between the cathode and the anode. See, when this photon, okay, so arrives at the metal surface, so this photon will cause the electrons to be emitted. Okay, I think the second batch can come down to sign. So you can, when the electron arrives at a metal, when the photon arrives at a metal surface, which is the cathode, so the electron will be emitted. Okay, for the remaining lectures, which is Friday, and for the next week lectures, the sitting, okay, so I wanted to be in this order. Physical science 1 will be here. Physical science 1, physical science 2, 3. Okay, so 1, 2, 3. 4, 5, 6 over here. Okay, and physical science and physical science 7 will be here. Okay, and then next week, okay, so this physical science 1 will go behind, this one will come in front. Okay, just change the position. Okay, to be fair. Lah. So the one always the so then you change. So here also change. So physical science 5 and physical science 2 will remain at the same place, middle. You are always in the neutral. Okay, so take note. So this is for Friday. So for next week, okay, so same, okay, but then you change the position. Okay, take note, huh? Okay, and then so now I'll give you a notice. Then because when you sit it like this, then I will also take a picture of each group. Okay. Okay. So come to keep it as a remembrance lah. Okay. So come. So let's move on. Oh, afterward, okay, we have this group to sign. Okay, so I just explain a bit. Okay, so then, so here, when the photon arrives, the cathode is actually what we understand as the target metal. It's a target metal. So it is the substance. So when the light photon arrives at the target metal, if the energy is enough, then it can cause the electron to be emitted. When electron is emitted, so electron is going to move from cathode to anode. So when there is an electron movement, meaning there is a current. Okay, so because electron movement, so it will produce a current. So this is what going to cause the emitter to be deflected. So if you look at the points, so the electrons from a current, okay, so form a current between the cathode and also the anode. So the current can be measured as a potential difference, okay, so as a potential difference. So the light frequency and the light intensity are varied. So the potential difference can be changed or reversed. Okay, so we can actually reverse the potential. So instead of negative on your left, positive on your right, we can actually reverse it. So by this, we know. See, we cannot, as I mentioned, we cannot see the electrons. But how do we know there is electron emission? When we look at the emitter reading, the moment emitter gives us a reading, that means there is a current flow. Why there is a current flow? There is an electron flow. Why there is an electron flow? These electrons are emitted by the metal target. Why is being emitted? Because of the energy that comes from the photon. That is the continuous understanding that can be formed to explain about the photoelectric effect. Okay. So here, this is looking into more specific into the photocell of the electron emission. Okay, so can I have the last group to sign first? So now you look at this equipment. So I have to explain to you the one. So now look at this. See, so now you all have to come in front. Where's your class? Mm. Oh, that end, right. Sorry for the inconvenience. Okay, so let's another 10 minutes, then I will give you a break. Okay, so the circuit to study the photoelectric effect. So now you can see more detail. Here we use usually when you use the photon energy electromagnetic ray, we try to use a specific wavelength, okay, which is what we understand as the monochromatic light. So which has a specific energy. Specific wavelength means it has a specific frequency. When it has a specific frequency, it has a specific energy. So E equals to HF. So this, when the specific energy is directed to the cathode, which is the metal target. So if the energy that is carried by this photon, so now I use the word photon. So I just don't want to mention wave. So we are doing the quantum physics. So then you will get familiar. So when this photon energy from the electromagnetic ray arrives at the metal surface, and if this energy is able to overcome the minimum energy required for the electron to escape, then the electron escapes from the metal surface, and we can see there is a emitter deflection. See why I mentioned there is a minimum energy required. See this minimum energy required. So for example, we use a particular frequency. you try to use a frequency of a range of frequency. This was the experiment that is conducted. This was the experiment I conducted, okay, so during my first degree, okay, so first semester of my physics. So we use different sources of laser, but it has a different wavelength. And we analyze not all the frequency is able to give, we can cause the electron emission for particular sample of metal. Okay, so a different metal will have may require different energy for electron emission, minimum energy for the electron emission. So this is found from the experiment. So we see that after a certain specific frequency, only electron is emitted. I mean, we can see there is a reading, emitter, deflected. So that explains there is a certain amount of energy that is needed for the electron to be emitted. So that's how Einstein have come to a point to state that there is a minimum energy required to cause a photoelectric emission. So not all range of frequency can cause the photoelectric emission. This is one of the prediction that is given by Einstein, which was not covered or not stated, explained by Newton. Okay, so that's why it is a classic. Then you have the quantum modern physics. Okay, so look at the arrangement here. When we apply a potential across the anode and cathode, so it is trying to basically accelerate the electrons. So when I apply a positive potential at the anode becomes positive potential, then it is going to attract these electrons. So the electrons are going to be accelerated towards the anode. For example, suppose in electric field, you have studied this. When electrical work done, EV, this is the electrical work done, all right, okay, here, EV, this comes from, we know that potential difference is equivalent to work done per unit charge. Therefore, the electrical work is equivalent to the potential difference multiplied by charge or charge times the potential difference. But here, when you are talking about electron, so therefore, the charge, we use the symbol E and the potential difference V. And this electrical work that is done on the electron has been converted to gain in kinetic energy. Have you seen this formula? In electric field? Got it? So this is what happens. So whatever the electrical work that is done, okay, so it has been converted as form of kinetic energy for the electron to move. Okay, so since the electron moves, so you can see there is a deflection in the emitter. Okay, fine. Any questions on this? Okay, any questions on this? Can you understand that? Okay. So this is giving you a very basic explanation on that. So this is another way of saying, just now you see from the side view. So now you see from the top view. So from the top, okay, same like the monochromatic light arrives at the cathode, which is the target metal. Electrons is being emitted, electron is being accelerated towards the anode. Okay, so because you can see the potential, we apply positive here, you have apply negative here. So therefore, fine. So the electrons are being accelerated. Okay. So this was a, there is a link because I opened the PDF. Okay, so I will not able to go to the link. Okay, so maybe I will run this when I do the lesson, because if I start now, so it is going to interrupt the recording. Okay, so then the sequence. So therefore, I will explain first. So maybe in the when we start the Friday lesson, I will start off with to show this first. the animation on that, and then I will do the start with the recording session. Okay. So if you look at this experiment, or you can also try your own. Okay. So the simulation link is there. So through this, you will be able to vary the wavelength. Okay. First thing is, if you look at this, you are able to vary the wavelength of the monochromatic source that you use. And by varying the wavelength, you are able to see, okay, so the electron emission. This wave pulse is actually the photon. That's the photon energy. Lah. So when the photon energy arrives at a metal surface, the dot that you see here is actually the electrons that is emitted from the metal surface. But it will be moving in opposite direction. So electrons are kind of emitted this way. Okay. Maybe after the break, we can actually, even after the break, I can try to show. Okay. So the electrons will be emitted because Friday main is too long already. So better I show it go. Then we can also vary the brightness. The brightness is actually the intensity of the light. Okay. So the intensity of the light, okay, so we can be varied. So intensity of the light have an effect. Wavelength also have an effect, but the effects are different. Okay, we will talk about that. We can also vary the potential difference between the anode and also the cathode. And this potential difference can be also reversed. Instead of anode being positive, I can also cause anode to be negative. Okay. So that can be varied. So this is to further investigate to determine informations about the kinetic energy of the electron that is emitted and so on. So that's the link for simulation later. Okay, so because I have to open up the PowerPoint. Okay, then from PowerPoint I can link straight. So this one I cannot. When I click, okay, so I cannot. Okay, so move on. So that was some things about the photoelectric effect. See, here we have some of the point discussion. So in the photocell circuit, a circuit to study the photoelectric effect. First point, the tube is vacuated, okay, so vacuum, so that electrons will not collide with the air molecules, obviously. Okay, so even in electron gun tube, okay, so we need to ensure the tube is vacuated. Okay, otherwise, whatever the particles that is emitted is going to collide with the other particle and is going to lose some energy, and it can be some other reaction takes place, ionization and so on. So we don't want that to happen. When a monochromatic light of a certain frequency shines on the cathode, photoelectrons are emitted. Yeah, so we have seen that. The electric field between the anode and cathode accelerates the photoelectrons towards the anode. Follow the equation I mentioned just now. Electrical work done is being converted to gain in the kinetic energy. Okay. Then the photoelectrons reaching the anode will complete the circuit and current. Okay, so the photoelectrons reaching the anode will complete the circuit and current. So the current that is produced in this experiment, we call it as a photocurrent. Okay, so because it is produced due to the photoelectric effect and will be detected. How do we know? Okay, so that is from the actually, we don't use ammeter. We use a microammeter, at least a milliammeter, because the magnitude of the current that is going to be produced is going to be very small. So when you use an ammeter will not able to detect the current. Okay, so we have to use a microammeter. So if there is no current detected, okay, so it means no photoelectric emission have occurred. Okay, that will be the conclusion. You see quite a number of students are online. That is the negative impact of having a lesson, okay, so which is runs online, okay, so because students take the uh, privilege of that, okay, and then lessons when it's been recorded, okay, so if you miss, okay, I mean everything there is a pro and con, okay, so otherwise, so like when you go to nowadays, I don't know how about the university thing. In universities, during my time in university, okay, so I mean, there is no recording session. Okay, so whether you attend or you miss the session, you find a way or you go and see the lecturer and get the information. Okay, so photocell circuit observations. So from this experiment, so what is the observation? First, there is no emission of photoelectrons if the frequency of the light is less than the certain critical frequency. So they have found out that there is no emission of electrons when the energy of the photon is lesser than the specific energy. So when you say it is lesser than the specific energy, that means it is lesser than a lower than a certain critical frequency. So that frequency is known as a threshold frequency. So a threshold frequency, now when you define it, a threshold frequency is the minimum frequency needed, okay, so for the photons to cause the photoelectric emission to happen. So this threshold frequency is the minimum frequency, okay, which leads to the energy, okay, so which holds the electrons inside the metal. If I'm able to provide an energy equivalent to that, at least I can I can free the electrons. So the electrons can free themselves. And if anything that is slightly more than that, the electron have an energy to escape from the metal surface. So the maximum kinetic energy of the emitter electrons depends on the frequency of the light and does not depend on the intensity of the light. So that's why we have a brightness and the wavelength to change. So by trying to do an experiment varying the frequency, keeping the brightness constant, then you keep the brightness constant, okay, I mean, you keep the wavelength constant, you change the brightness. So they have found out that they came to a conclusion, the maximum kinetic energy of the electron emitted is dependent on the frequency, independent of the intensity of the source that we use. The emission of photoelectrons, so that is the 2 points. So this is actually called as predictions of modern quantum physics. These are the predictions that has been explained under the modern quantum physics. So the third one, the emission of photoelectrons is instantaneous. No delay time between incident of light and emission of electrons. So instantaneous, that means the electrons will be emitted immediately the moment photon arrives at the metal surface. It's not that the photon will, when photon arrives, the energy is like absorbed until certain time, then only you have electron emission. No. So the moment the energy arrives enough, electron will be emitted. Otherwise, no. It will not accumulate. And the last one is the rate of emission of photoelectrons is directly proportional to the light intensity. So meaning the rate of emission of photoelectrons, that means the number of electrons that is emitted. They found out that the number of electrons that is emitted from the metal surface is directly proportional to the intensity. And if you did the experiment uh, yesterday, I mean the experiment on what's that? The radiation, you have seen the formula. Intensity is equivalent to power arriving normally per unit area. So intensity is proportional to the power. So that means when the intensity increases, the power increases. When the power increases, So you are expecting the amount of electrons that is emitted from the metal surface will increase. But it does not affect on the kinetic energy of the electron emitted. Just the number of electrons emitted, okay, so will be increased. That's all. Okay, so these are the 4 important predictions that has been concluded from the modern quantum physics experiment, which is led by the Sir Isaac Newton. Sorry, Sir, what's that? Einstein. Okay, so Albert Einstein. Okay, so we will take a break now. You can visualize these points first. Okay, thank you. Later you ask me why I just want to go back. What's more? Oh, this side, this side. Hard one. So, I don't know. So now, then, I don't know why you use this formula. Why she over T and 5T？ 因为它有两个嘛，一个是什么 RT 跟一个是 NKT 哦，跟 RT 跟 NKT，因为你都没有学 RT 跟 NKT 都一样，二分 NKT。OK，其实讲你用我那个 NRT 也是拿不到这个。哎，那找你不说的，这是我 NQ PV equals to， 我都没有，你没有 pressure， 都没有给你 pressure。然后我那个 PV 可以换成 NRT。对，所以你用 Q 等于3/2 NRT。那这个 N I don't know why. What do I do instead？ 你用这个什么？我这个，啊，你没有 P 啊？对。哇，跟这个 N 怎么样？我来理解。它不是，见过不是？它没有一个大 N 的，它是见过了，一个江或者是见过了 NKT。因为我这个是从 somewhere else derive 的，这个我是从 which this is to consider all three dimensions. Oh yes. And this square equals to 2/3 and equals to equal to 2/3 and half of this square. What's the teacher? Yeah, what's the question? No. Okay, welcome back, students. Just to run through the 4 points again. So the limitations that has been observed from the classical and proved by Einstein, which comes under the modern physics. So where we have identified that, so found that no electron emission, the emission of photoelectrons, if the frequency of the light is less than a certain frequency, which is known as the threshold frequency. So threshold frequency is the minimum frequency of the photon that is required to cause a photoelectric emission. Second, the maximum kinetic energy of the electron emitted is dependent on the frequency of the light, which is frequency of the photon that is directed to the metal surface. Okay, so and it's independent of the intensity. You increase the intensity, but the frequency is low, no electron emission. The emission of the photoelectrons is instantaneous, no time delay. So electrons will be emitted immediately after the photon arrives at the metal surface. And the last one, the rate of emission of electrons, which is the number of electrons that is emitted. It is dependent on the intensity of the light, not the frequency of the light. Okay, these are the 4 predictions. So predictions, okay, wave theory. So electrons can be emitted by all frequency of a light used. This was the wave theory. Okay, so what has been predicted in the earlier by Newton. So all range of frequency can cause a electron emission. It has been proved wrong. Then emission of the photoelectrons cannot be immediate. Okay, so because the electrons need some time to collect, absorb, and to have enough energy. No, it does not happen like that. It's not like boiling water. So when you heat the water, is the water boils immediately? Do the water boil immediately? No, it has to absorb the heat. So the heat energy absorbed until the temperature rises to 100 degrees Celsius. Then only the water will start to boil. Okay, so that is in the case of the water boiling. But that is not the same case here. So in the case of electron emission, the energy is not like absorbed until a certain point, then only the electrons are emitted. No. Whether, okay, so the electrons receive enough energy. So the moment they receive enough energy, the electron are emitted. They will not accumulate. They cannot store it. Okay. And the maximum kinetic energy of the photoelectron should depend on the light intensity. No, it does not depend on the light intensity. It depends on the frequency of the light. So all this has been proved. So here is just to show. Okay, so figure 1, 2, 3. Okay, so basically when you're referring to the electron emission, okay, so it is not that when you have more. Okay, so what in further detail? Okay, so diagram. No need to follow that. So basically, this is the three things. One, which is wave theory. Okay, so which has been proved wrong from the modern observation. Okay, so according to the Einstein's explanation, Einstein extended the work of the Max Planck on the quantized energy. So quantized energy is quantized mean it is in a packet, a discrete energy level. So light of frequency f consists of discrete quanta, each of an energy of E equals to hf. Each photon travels at the speed of a light. So light quanta are emitted or absorbed on an all or nothing basis. So a substance can emit 1, 2, 3 quanta integer, but not 1.5. So similarly, an electron in a metal cannot absorb half a quantum, but only an integer number. So when you are referring to the amount of energy that is absorbed, it is also in an order of an integer of a number. It cannot be in a fractions. Okay. So a light quantum, okay, when absorbed by the metal, delivers its entire energy to one electron. Okay, so when this energy is absorbed by the metal, okay, so that particular photon energy, it is used by a particular electron to escape. So that's why when the power increases, the intensity increases, then the energy can be distributed to more electrons. So therefore, more electrons will be emitted. Okay, so that's the idea. But then that does not cause the kinetic energy of the electron emitted increase. No. So the intensity increase, power increase. So the power that is arriving normally per unit area is what the intensity. So power arriving normally per unit area increases when the intensity increases. So more electron gets shed, they can escape. Okay, more electrons are emitted. So this is just to uh, put it in a diagrammatic way. Molecules of a radiating object E equals to HF and HF integer. So that energy, okay, so radiation, uh, you have light emitted in packets of quanta, each has a energy of E equals to HF, as what stated by Max Planck. So these are the energy of the photons, okay, so which is radiated. So therefore, the total energy of a photon of a frequency f is E equals to HF. Okay, so then the frequency, frequency I can substitute with C over lambda. See, like just now, we did discuss about threshold frequency. So here we have a threshold frequency. But then we also know the threshold frequency, we use the symbol F naught. Okay, but the F naught is also equivalent to C over lambda naught, where lambda naught is known as the threshold wavelength. Okay, so lambda naught is equivalent to the threshold wavelength. So threshold frequency is the minimum. Okay, take note this. Okay, see, threshold frequency. I'm basically asking. Okay, see, threshold frequency is the minimum frequency required for photoelectric emission to occur. So how do you define threshold wavelength? So threshold frequency is the minimum frequency of the photon that is required to cause a photoelectric emission to occur. So what about threshold wavelength? How do you define it? So when I refer to F naught, which is the threshold frequency. So this is defined as minimum frequency of photon or light required for photoelectric emission to occur. So that is for threshold frequency. What about if it is threshold wavelength? What about threshold wavelength? Anyone? Ali? The sentence almost the same, but a bit.
大筒位正确放置，正在连接。
哎，
大筒位正确放置，正在连接。开始连接话筒。已解锁，请取出话筒。
okay. So, how you explain the threshold wavelength? Yes. Okay. So when you refer to frequency, okay, so from the formula, we know that E equals to HF naught. E equals to HC over lambda naught. So they say in case when you are referring to this energy that is arriving to the metal surface, so this is the minimum frequency. So meaning inside the metal, okay, there is a energy. It has been not mentioned here yet. So it is later we will be looking into that. So it is known as the work function. It is known as the work function. So the work function is the energy that holds the electron inside the metal. So therefore, in order for the electrons to be emitted, the energy of the photon or the light must be at least equivalent to the work function. Then only it can overcome to cause the electron to be emitted. And the formula for the work function, it is given by H and naught. So that is your threshold frequency. So meaning, if the energy of this, so here I don't put F naught. Sorry. So here the work is equal to HF naught. So meaning this frequency of the light has to be greater than the work function, greater than the threshold frequency. Then there is enough energy for the electron to be emitted. So if I were to write that, okay, here for the electron to be emitted, the energy of the frequency of the photon must be greater or equal than the threshold frequency. So it must be greater or equal than the threshold frequency. Then only there will be a photoelectric emission. Okay, so this is a work function. Work function is calculated based on the frequency, Planck constant multiplied by the threshold frequency, minimum frequency which is required for the photoelectric emission to occur. So therefore, when the frequency of the photon in the light is greater or equal than the threshold frequency, so there will be a photoelectric emission. So the definition for threshold frequency is the minimum frequency required for the photoelectric emission to occur. But if I put it in terms of wavelength, so this will be Hc over lambda naught. So they are inversely related. Therefore, if I'm going to define the threshold wavelength, it is the maximum wavelength of the photon or light required for photoelectric emission to occur. So okay. So in this case, now I have introduced energy of the photon. I have introduced the energy that holds the electron inside the metal, the minimum energy, which is known as a work function. And over here, when the energy of the photon that is provided, energy of the photon provided, if it is greater than the work function W. Sometimes the work function W, they also use a simple sigma like this. So it's the same. Okay, you can use a simple sigma, okay, or W for the work function. So in that case, when the energy of the photon is greater than the work function, the remaining energy will be the kinetic energy of the electron to escape. So I have 1, I have 2, I have 3 energy here. So when I combine all these 3, that will give me an equation for the Einstein's photoelectric equation. Okay, so that will give us the Einstein's photoelectric equation. So here, this is what I was mentioning just now. Okay, so when the energy, okay, so arrives able to overcome the work function, so the W, that the work function, that's the minimum energy required for the photoelectric emission to occur. So the electrons can be emitted with the kinetic energy. So here is what I have mentioned just now. Okay, so I wanted to tell that. Okay, so before, okay, so I go to the slide, okay, for the repetition of explanation. So threshold frequency is the minimum frequency of the light that can emit photoelectrons from the metal surface. So here you have F naught equals to W over H, or basically your W, okay, work function is equivalent to HF naught. Okay, so Okay, so W equals to H F naught. So work function is the minimum energy required to remove an electron from the metal surface to overcome the attraction, force. Okay, so that is experienced by the electrons inside the metal. Okay, so I think yeah, just by picture. Okay, so whenever the energy of the photon is greater than or equal than the work function, there will be a electron emission occur. So that will happen when the frequency is greater than the threshold frequency. See, over here, you have different metal and work function. So you can see that different metals will have different work function values. So because like when you refer to different metals, from the chapter nuclear physics, you understood that the nucleus will have different number of protons and also neutrons. So when they have different number of protons and neutrons, so then the arrangement of the charges, okay, so it is different. The density of the atoms inside will be different. Therefore, okay, so the amount of energy that is needed for the electrons to escape, definitely will vary. So that's why different metal will have they have their own work function values. So not all frequency, I mean, just say for particular metal, okay, a specific frequency can cause a photoelectric emission to occur. But I cannot expect the same frequency can cause a photoelectric emission for the other metal, because the other metal probably have a higher threshold frequency or higher threshold frequency. Okay, so you can see silver, the threshold frequency is threshold work function. I mean that definitely different threshold frequency. So the work function is 4.26 eV. 4.26 eV mean 4.26 you times by 1.6 times 10 power minus 19. That will give you the answer in joules. Okay, that's to convert to joule. Otherwise, 4.26 is in the form of EV. So you can see lead, aluminium, gold, copper, sodium, cesium, and potassium. Which one has the highest? So obviously you can see it is in the descending order. So silver has the highest work function. So it requires the most energy to cause, oh, sorry, not silver, gold. So gold has the highest work function, correct? 5.1. Yeah, so therefore, gold requires more energy to cause a, we need more energy to cause a photoelectric emission to occur for the gold. Okay, but don't worry about these values. Okay, you will not asked to, there will be no questions whereby you need to use the work function to solve, but the work function value is not given. So it will, if you need to use, it will be given in the question. Otherwise, you need to find out the work function of a metal based on other information that is provided in the question. So this is what I was saying. Eventually, it will come to, when I relate 1, 2, 3, the energy of the photon, so the energy of the photon, the work function of the metal, and the maximum kinetic energy of the photoelectron. Okay, so the maximum kinetic energy of the photoelectron. So therefore, that forms an equation based on principle of conservation of energy. So based on principle of conservation of an energy, so we have the Einstein's photoelectric equation. Okay, so and you can actually rearrange this equation. If you bring your work function to the left, meaning the energy of the photon minus the work function will be equivalent to the maximum kinetic energy of the electron that is emitted. So the energies can be given in form of EV or you can work out in joules. Okay, so I suppose you know how to convert that. So, and further, okay, so we can see HF. So if you want to convert this into electron volt, then you have to divide by the charge of electron. So then all will be, so like this is in joules. So from joules, if you want to convert to EV, electron volt, you need to divide the charge of electron. That's it. So that will give you the things in the electron volt. Okay, so I think this one I did mention. I don't want to go on this. Okay, so example 1 and 2. So could you please do example 1 and 2? Over here, okay, you can see a graph. This was the experiment I was referring to. So we can conduct an experiment for this, and you are able to plot a graph for the kinetic energy versus the frequency. And from the graph you plot, we can actually find the constants. The constants is, okay, so when you plot a graph kinetic energy versus the frequency, we get a straight line with a y-intercept. So the gradient of the graph will give us the, what is the gradient of the graph here? Planck constant, yes? So the gradient of the graph gives us the Planck constant. And when you find the y-intercept, so the y-intercept will give you the work function of the metal. But how to determine the maximum kinetic energy of the electron that is emitted? See, because we cannot be finding the speed of the electron. Out, we can't even see the electron. So how to determine the speed of the electron? So there is a way, mechanism you work to find the, not to find the speed, to find the kinetic energy of the electron. Okay, so that we will look into the next class. So if there is, if you have time, okay, so please just try to go through that. Okay, so then I will continue from there. You can see there's a lot of diagrams. Okay, so therefore we will be able to accelerate faster. But I mean, I will give the explanation. So take note, example 1 and 2, I want you to do it. Okay, so when you come in for the next session. Okay, so with that, thank you.
So is it the solar energy is based on the electric,
Huh?
like solar energy?
Uh-huh.
Is it based on the photoelectric, like the sunlight, light on the board, and then
No. No difference. Because solar energy, it goes to the solar panel. So the solar panel have a detector. It will detect the heat. That heat will be converted to a electrical energy.
also is a thermal electric.
Yeah.
Function.
So this one is different.
Then I saw that this emit electron can
No.
be used to produce current.
No. That current is a very minimal current that is produced due to the electron flow. But that is not the energy stored to produce electrical energy.
So not enough, less than
Yeah.
the teacher.
Yeah. For this one, then this one. You are the one who school vacation. No. Yeah. There's something, what is N now? How to find N? I think that's because the student asked question on the, okay, yeah, come in. Okay, so total energy. Yeah. One comes from where? And you from the yes.
For the cake evaluation, I did not submit and I already emailed you 2 days ago.
Okay, you have emailed emailed me.
Yeah.
Okay. Yeah, I received. Sorry. If you have sent to the Teams, okay, so I will be immediately can give a thumb up.
So I will just send
Better.
Okay.
Easier because
Okay.
here and there very difficult for me to
Okay.
address.
Sorry.
Yeah, you just you just send it to the Teams. Yeah.
Okay, thank you.
So it comes from this, right? Then
PV equals to 1/3.
Q is the total energy.
Total energy. This one is from the part of ideal gas, isn't it?
Yeah.
But that equation like this, because PV equals to 1 over 3 Nm mean square speed.
Yeah. EV equals to 1 over 3 and half.
Yes, girl? You have anything to ask?
So
Hmm?
it's just then
Oh.
both sides. So, yeah.
But 1 over 3, but then this one is what? 1 over 2. This is wrong already. This is not the correct equation. The equation will be like this. PV equals to 1 over 3 and PS all like this. Yeah, mean speed lah. Okay, or sometimes you see that like sine of no. Then if you pick this out, okay, MP squared, then yeah. Then you have to bring if you are bringing in the but what do you want to find? What do you want to find? Why you want to do that? But that one you can use this formula, right? Okay, so you can use your half and it's actually equivalent to 3 over 2 kg, right?
Yeah, but then I want to derive it. Yes.
But do you have the information pressure and the volume in the case here?
No, but then TB can be converted to NR here.
Oh yeah, so I mean, you're trying to make this complicated. This is already been proved. By comparing this with PV equals to N RP, you already get this. You can just use this straight one. So this average kinetic energy is this equivalent to 3 over 2 kT. So you just need to know the temperature inside Johnson. And temperature has to be in Kelvin. So you don't go this way. So this is the so from this two we are already proved this, and we will use this to solve the problem. So because we don't break up from here. See what I understand what you did. So you did PV equals to this thing you make it like sorry, and you bring it out. So this one is M. Okay, so then half. Okay, so then it has to be 2 over 3.
But then yeah, cannot be right. This one.
Cannot. Once you open up like this, then because in order to derive to this, it is between this equation and this equation. This two equation was used because PV, they are same. So meaning 1 over 3 and mean square speed is equal to N RT. But then here you need to just checking any teachers waiting to come in. Okay, so this N is the number of mole, N divided by the Avogadro constant, and gas constant is equivalent to the Boltzmann constant multiplied by the Avogadro constant. Cancel. That's how you get NKT. Okay, so then this N and this N will cancel. So then when you look up, you will get to this equation. This is a process to prove to this. This way down.
So compare this to this.
Yeah. So here you will have 1 over 3 and goes to KT. So therefore, I multiply 3 over 2 here, 3 over 2 here. So when I multiply 3 cancels, so I have half mv squared equals to 3 over 2 KT. So that is equivalent to the half mv squared. That's how you get it in the equation.
Okay. Yeah.
Okay. So this one, you may see this has been shown in your notes, but if you derive here, then you are stuck. You cannot move to this.
That's it.
Yeah.
Because I try to put here.
So here
But yeah, I didn't think about this can be connected.
yeah, because it's PD, I say, so you can equate that. Okay.
This is follow the next 3 lecture class.
Yes. So next lecture we follow this. Next week we shift this.
And then
Next Friday is a public holiday, so I need to do a replacement. That's why I need to check whether we can do a replacement on Wednesday. Okay, so Wednesday you will have 2 sessions lah. So one will be morning, the other one is in the evening. Okay. But the Wednesday, the evening one will be also a recap and give some advice for the exam. Advice.
Thank you, teacher. Bye-bye.
Okay, bye. See you.
So next Wednesday also, like, this 3 different, like,
Yes.
at morning and after session also stay in this stage. That's my friend always asking me a lot of things.
Okay. Because in the last 2 weeks we don't be in attendance. So because now they will generate all the barring everything, they will generate and send. For me, I want to know who are serious students who are attending the lesson. So I know, so roughly I know who are being serious. That's why when I come in also, I will observe who are the students who come in before me. Okay.
正在关机中，Shutdown in progress。
You are came in for next class, isn't it? What's the next subject?